And this is a picture of the tunneling microscope that I have in my laboratory, I had in my laboratory. And this is the little robot that moves around a metal tip, which is the equivalent of, does the same scanning of the surface as our fingers did at the back of our hand, but finer. This is about the width of your finger right here. And it is really an extraordinary instrument. Welcome to my world of atoms. Let me just tell you what you're looking at. This is a picture of some platinum atoms. Each one of these bumps is a single platinum atom on the surface. Here's a bunch of xenon atoms on top of a metal surface. The xenon atoms have come together to form a little, we call that a little raft of atoms on the surface. And here's some xenon atoms sitting on top of a step edge, looking out over another plane of atoms down here and a higher plane of atoms up on the top. Atoms used to be really, really small things that nobody had any access to, nobody could play around with, nobody could see with any kind of instrument. That's changed. Atoms are now a huge thing. Look at this monster. It's gigantic. That's a xenon atom. And xenon is my favorite atom. Sorry, Argon. So one of the things that we learned to do in our laboratory was to take this tool, which was invented for imaging, to be kind of our eyes to the world of atoms. We learned how to use it as a set of hands, allowing us to manipulate individual atoms. Let me show you how we do that. We take advantage of the fact that atoms are sticky. Now, is it important that atoms are sticky? I think so. And the reason is, what do you think would happen to me right now if atoms were not sticky? Anybody got an idea? I would fall apart. My atoms would just take off and go everywhere. So every morning when I wake up and I find that I'm still intact, I think that's the coolest thing in the world, because atoms are sticky. Right? So that's actually really important, because that's how we use the microscope to manipulate atoms on a surface. What we do is we bring the tip down so close that this atom on the end of the tip begins to stick to this atom on the surface. And when that's the case, if we then take the tip of the microscope and we move it sideways, guess what's going to happen? It's going to drag the atom with it and bring the atom to a new location. And then if we want to leave the atom here, what do? We just take the tip and we pull it back. But it leaves the atom on the surface because these bonds here are stronger, or if you like, stickier, and that leaves the atom in a new location. What's really cool about that is it allows us to take atoms and put them where we want. Now, the first thing we did was to write out IBM. I'm very proud that I got the spelling right. Extremely proud that I got the spelling right. But think about how we do things. We design and build things in our lives to do things that we think are useful. So, for instance, somebody had to design and build these chairs because it's useful to sit in a comfortable way. Imagine all the useful things that you could do with atoms and molecules if you could put them where you want them to go. Here are some molecules that we built by taking the individual atoms, just like building blocks, and snapping, just like Lego, and snapping them together. Right? But what's really neat about this is these molecules cannot be built by any other means. They're quite unique molecules. These are molecules made from two different kinds of atoms, from cesium atoms and iodine atoms. And we play with them just like Lego blocks. They snap together in particular patterns, and we bring the individual atoms in, and we snap them in place, and we can form these really quite amazing structures. We learned how to build these things called quantum corrals, this circular ring of iron atoms on top of a copper surface. And what you see in here are a bunch of waves. What's really special about this is these waves are just due to the electrons on the surface. So it allows us to explore how electrons behave inside of very, very small structures. We also went on to build the world's smallest computer circuits. These are very special circuits. They don't operate like normal computer circuits. They're made from carbon monoxide molecules on a metal surface. But what's very special about these circuits are how small they are. They're much, much smaller than what we use in our current technology. So the tunneling microscope allows us to explore new ways that we might build computers. And for those of us in IBM, that's very important, of course. So what I want to do is, to get lucky, I want to try to run our tunneling microscope from here. The tunneling microscope is over in California. And the way it's going to work is we have the tunneling microscope in the laboratory in California. It is controlled by the computer in the laboratory in California, which is connected to a computer which itself is then connected to the internet, which is connected to my laptop here. And so from my laptop here in the auditorium, I'm going to try to connect all the way back to the microscope in California, and we'll see how that goes. There's the laboratory in California. That's the connection from San Jose to Boston. And just to make it a little bit more lively, I think what we'll do is let's call up the guys in the lab in California. Ooh, I love that sound. This is great.
Hello.
Hey, Chris, can you hear me?
Hey, John.
Hey, this
Yeah.
is Chris. Say hello to the audience.
Hello, everybody. Would you like to examine some atoms?
Yeah. So are we ready to go?
Ready to go. Start it up.
All right, let's try. So I'm going to go to the website. All right, let's try to log on. Okay, so this is an image of the actual tunneling microscope in the lab, or the room temperature part of it. The microscope is in very good vacuum and at very low temperatures. And this is to simulate some of the instruments in our laboratory that we'll be using. And then we'll see the images showing up over here. So let's see if we can scan over the surface by pressing on the scan button. The microscope, the whole apparatus is about, I guess, about 14 to 15 feet tall. But the microscope part of it is just a little tiny thing. Everything else is what you need in order to achieve these conditions. Welcome to the world of atoms. Let me describe to you what we're looking at. The tip is scanning across the surface, and every time it goes across, it comes back, and then it goes across, it comes back, and it does this fast, as fast as what you see here. Just like your finger went across your hands, and it had to go up and down to go across your hand, the tip has to go up and down across the surface, and you can see the trajectory of the tip in the virtual oscilloscope over here. And then, over here, we're seeing the area that we're imaging. I'm guessing that it's about 8 nanometers by 8 nanometers in size. It's roughly about what it is. And the grayscale that you see here is being applied as if there was a light source shining from left to right. So these are bumps on the surface. And you can see the bumps show up over here. But let's take a look at the 3D way of looking at the surface. So we'll press our virtual 3D button over here. Right? And we'll ask the computer to take the same information that you're seeing over here and display it so you can see the individual bumps on the surface. Today, we have a surface which is made out of copper, a pure copper crystal. And on top of that, we have both cobalt atoms and copper atoms. I'm not sure which atoms we have that we're looking at right here. These might be copper, they might be cobalt. Well, that's Chris. Maybe he knows. Hey, Chris.
Yeah.
Are those copper atoms or cobalt atoms?
Copper atoms.
Ah, thank you. Copper atoms.
Sebastian picked out 4 atoms for you. Is that what you see?
Yes, that's what we see. It looks very good. And they're looking really quite nice, I must say.
Well, they're individually selected.
Ah, thank you. Okay, so I think what we should do is try to move one of these guys. What do you think? Is that a cool thing to do? All right, we'll give it a try. All right, so what I'm going to come over here is I have to come and tell it that I want it to finish scanning. So I'm going to press the Finish button. And then we'll wait for it to finish this image. So it keeps on scanning over and over and over again. Oh, and it stopped. Okay, then what I need to do is I'm going to have to press this Move Atom button. Now what's happening is the tip is no longer scanning across the surface, but the tip is located right here. Now remember, to move an atom, we have to put the tip over the atom and then bring it close to make a sticky bond to the atom. So that's what I'm going to do. I'm going to go to this atom that's up here on the top. Okay, now the tip is up high. Now, with the next click of the mouse, what I'm going to do is lower the tip down towards that atom on the surface. Oh, it's down. Okay, so, oh, that's a good sound. I'll tell you about that sound in a moment. So let's try moving the atom down this way. I'm controlling where the atom goes by using the mouse on the computer here. That looks like a good spot. One more click. And pull the tip back, and now it's going into the scanning mode. So you see how easy it is? You just press some buttons, you just click and drag, and you move the atoms around. Right? These are real sticky atoms. If we brought two together, they would form sort of a two-atom kind of molecule that we wouldn't be able to take apart. So I'm not going to go do that right away. But there you see it. Real atoms, this is not a simulation, in San Jose, California, about 3,000 miles away, inside of a vacuum chamber, cooled to nearly absolute zero temperature. It's actually about 4 degrees Kelvin. There's a piece of copper. On top of that piece of copper, there are 4 atoms, and we just moved one from up here to down there. Now imagine what you could do with that. If you could put atoms where you want them to go, where would you put them? What would you learn? There'd be all kinds of things to do. Being able to do that is not only really valuable in terms of how we advance science and our knowledge, but as you've seen, it's great fun. Thank you for being a wonderful audience. The microscope's up and running, so if you want to come up and try moving an atom, I'd suggest come on up. We'll give it a try. I'll bring it back right there. Okay, left leg. It's gone. You moved an atom.
Yeah!
Score, dude. You did it! Yay!